the one that actually has the iLearn input grades, but it's the same test, so it doesn't matter when you downloaded the test, it's the same test. So, I was going to show you.
Do you have a time estimate in comparison with just not just like hours, but with comparison to the other ones?
Yes, more or less.
You know, it's hard to say. I'd say it's fairly similar.
To the second?
Probably to the second.
Okay, because there was a big difference between the first and the
Yeah,
second.
more like the second. I would say.
Cool.
And I'd say it's probably a little more straightforward than the others.
Oh, yeah.
Yeah.
This homework's a little more
It looks a lot longer. Like the other one had like 34 questions, and this has, I think, like 45. But it's not that bad. Like it's a lot more short questions. Okay, so this is what it looks like.
Is it all logistic progression then?
Well, you have one logistic regression and then one two-way ANOVA. So this is what it looks like now. So the picture was gone before, but everything else is the same. So, and then just put your answers in here. I like your pie chart. Thanks.
So here's my pie chart.
Hey, that's actually nice.
Yeah.
I like that.
Okay. So I'm going to turn my email on. Okay. It distracts me when I see all those things flashing up when I'm teaching. All right. So, sorry, I totally spaced your quiz, actually. I don't think I could have gotten it done anyway because it's been really crazy the last couple of days. But, yeah, when I got in this morning and saw my frantic where's the quiz emails, I would have told you last night, except I forgot. So,
At least you know we were looking.
yes, actually,
That's true,
I think all but maybe just a couple of you sent me an email. So I was impressed.
I did not.
Impressed.
I did not.
I didn't.
By the time I sat down to do it, I already got your email. So like, oh, okay.
Yeah, not everybody, but I would say over half the class sent me an email, and I was like, good job, guys. So
I was gonna get like 3 points because we would have done it.
Yeah, like 100% on it?
No, they just had.
I'm just impressed.
50%. Not like out of 50, like half the points you would have gotten.
Okay. Down. Okay, how many, did you guys do the reading though? Did you look over it? It'll make it a little easier if you've gone over the reading. We're actually doing probability today. And this is actually the foundation of Bayesian statistics, but it won't look like what we did on Monday. So we're going to learn about a rule called Bayes' rule. And the rule was developed by Bayes, who developed Bayesian statistics. And it's, like I said, the foundation of everything he did. But we need to talk about conditional probabilities. We don't do a lot with probabilities. Those of you guys who took Brother Cromar's class, you've dealt with probability quite a bit. But there's no other place that we really deal with probability at the school. And in Brother Cromar's class, how much time did you spend with conditional probabilities? Like 3
I know they
years.
spend a lot of time with econ stats on it.
Oh, yeah, econ
We
would
did
have
more
a
in
lot.
Math 108.
I should say in the math department we don't deal with it much. I don't know about econ. So we're going to talk about what a conditional probability is and why it's important, and then we're going to talk about how Bayes' rule really helps us out. So to just do a brief introduction of what they are. Okay, so I have to tell you, first of all, fall semester, when I was putting this together, my husband was watching a show while I was making the slides, and he was watching Numbers. Do you guys know what that show is? Yes! And he happened to be watching the episode on Bayesian statistics, and I was like, how funny, while I'm typing out my Bayes slides. I love that show. So, that's kind of funny. So anyway, he's actually, I don't know if you've noticed, most of his mathematics is really statistics that he does. Almost all, not all of it, but almost all of it. So true. Anyway. So what is the chance of drawing a king off the top of a deck of cards? So I have a deck of cards, what's the chance it's a king?
1 out of 13.
4 to 52.
Yeah, 4 to 52, or 1 out of 13, because I've got 4 of them and they're 52. Okay, what's the chance that the second card is a king? Now let's assume we have not looked at the cards, they are all intact. What's the chance that the second one is a king?
Same or the same?
It's the same, because I don't know what the first one is, right? So it doesn't matter, it's still 4 out of 52. It doesn't matter that's the second one down. It has the same probability if I don't know anything about it. Okay, next one. Let's say you look at the first card and it's a king. What's the chance now that the second card is a king, now that I know something?
3 out of 51.
Yeah, 3 out of 51, because I now have 51 cards in the deck and I only have 3 kings left, right? Okay, let's say I look at the first card and it's not a king. What's the chance the second one is a king?
452.
Okay. Those last two are what we call conditional probabilities. It means that I know something now and I can use that information to update the probability. Does this sound a little familiar from?
Same idea.
Yeah, it's a similar idea, and this, this is kind of the crux of Bayes right here. Okay, so, like I said, so the notation. There is probabilistic notation that goes with it, and I'm going to use it. So, we want to know the probability that the second card is a king, given that the first card is the king. So the second piece is what I know, and the first piece is the chance I'm trying to find out. Then there's the probability that the second card is a king, given that the first card is not a king, is the 4 out of 51. And then, just as a reminder, the second part is the piece you know. That's the given. Okay, so given that, that's what the bar is. That bar is our mathematical notation for the word given that. So some examples of conditional probabilities in real life. The chance that a person has breast cancer given that she had an irregular mammogram. Okay, so a woman goes to the doctor, she has an irregular mammogram. Does that mean she has breast cancer?
No.
But now knowing that her mammogram was irregular, do you think that affects the probability she has breast cancer as opposed to before she had the mammogram and we didn't know?
Yes.
Yeah, okay, so now that we know it was irregular, that probability has changed. So this would be the chance that she has cancer, given that she had a positive test. The chance that an ex-convict returns to prison, given that they have a wife and children. So, do you think the fact that somebody has a wife and some children might affect the chance that they would return to prison after they get out?
Yes.
Yes.
Yeah, probably would. And this is the one, because I actually wrote this slide, and then 5 minutes later, on numbers, he was explaining this to his class. I was cracking up, because this is like one of the famous conditional probability ones. The chance that the prize will be behind door number 2, if you know it is not behind door number 1. So,
Assuming there's 2 doors.
so you have 3 doors. So this is the Monty Hall problem. Yeah, I should have explained. I'll give you the setup. This is like a super famous conditional probability problem where they would go, this was a famous game show called the Monty Hall Show, and they would have 3 doors, and behind 1 door is a great prize, and behind 2 doors is a goat. And so you get to pick a door. You say, I pick door number 2, and then they show you what's behind one of the other doors. That's a goat, the goat behind one of the other doors. And then you have the choice of changing doors or sticking with your door. And the question is, should you change doors? And actually, yes, you should. Do you get to the goat? I'm not sure.
I was going to say the same question.
So you
What?
can, like, I get a pet.
You get goat's milk. It's delicious.
And go crazy.
Or you
It's
could
like
kill it
my
and eat it.
My in-laws had a goat.
Let's Make a Deal does that too.
Yeah. It's used in different game shows. We use the same thing over and over again. But yeah, if you use the conditional probabilities, you can show that you're better off switching doors. I think you're a lot more likely to get the good prize if you switch doors. Okay, here's our example for math. This is this one is very interesting because of how it's done. But the ELISA test is a test that's used to screen for HIV. And I want to have you think through the problem because, like I said, these are practical probabilities that have real life use. Which one would be easier to get from gathered data? The probability that a person has a positive test, given that you already know they have HIV, or the probability that someone has HIV, knowing that they had a positive test? Okay, how would you get an estimate of that first probability? What would be the actual study you would do to get that number?
You'd have to get everyone that has HIV and give them a test.
Exactly. So find a whole bunch of people who have HIV, give them the test. That's your probability. How about the second one?
Just give the test a bunch of people and
Whoever tests positive, you check them if they actually have HIV.
How do you check if they have HIV?
You could just show them the test again.
But you're going to make some mistakes still.
Yeah, I know.
Which one do you think is going to be harder to get?
How did they know that the first people had the HIV?
Is it just because they live with it? And
Like they can gather people who are already known to have HIV. Like
Okay,
they,
first one's easier.
yeah, the first one's a lot easier to get. Okay. So, like I said, the chance that they have a positive test given HIV, you get a lot of people that you already know have HIV. And you give them the test. And then you calculate the proportion that tested positive, and there you go.
so you're just figuring out the accuracy of the test.
Yes. Because you are going to have some false negatives. There will be people with HIV that it misses. And that's true of every test.
Would you also test a number of people that don't have it and see if any of them turn out positive?
That actually has nothing to do with that probability. That would be a different probability that, yes, we would be interested in, but it won't help us with that particular probability. But, yeah. Okay, the next one, you have to get a lot of people from the general population, give them the test, and then that people who tested positive, they are now your population, and then you have to figure out which ones have HIV, but you can't really use their test to find that out.
Is there another test?
It would be really hard.
You just
So,
have time would tell on that one, right? Like you could test
you should go to test, and you can take blood draws, and you can do,
That was funny, like I
but first of all, how many,
So you pick their time.
Yeah.
which one is going to require more people up front?
This one.
This one.
Yeah, this is going to require way more people because you have to get enough people who test, enough people to get enough people who test positive to even run your study, right? So you're going to have way more people in this one, and then figuring out if they have HIV, not being able to use that test is going to be really, really tough. So this is the hard, definitely much harder to find. Okay, so we just went through all of this. Notice that they are not the same probability. And so which one, if you guys had to do one of those, which one would you rather do?
Knowing the HIV.
Yeah, given they have HIV, what's the chance they have a positive test? It's going to be way easier. Okay, question. So that one's easier to get the actual probability of. But now let's look at it from the doctor's perspective. The doctor has a patient come in. The patient is concerned that they may have HIV. So he gives them the ELISA test, and they have a positive test. So which probability is pertinent to this situation? Yeah. What do you know about the patient?
That they think they have. That the test is positive.
They have the positive test. And what do you need to know?
Probability they have
Do
HIV.
they have HIV? Because if you get a positive test, does that mean you have HIV?
No.
Not
No.
100%.
There are false positives and false negatives all the time. Okay, so we've already decided that, yeah, history.
Just from that, how did you know that the patient had a positive test?
Oh, I put it in there better. Oh, here we go. It's the second slide. And I was looking at it going, I left something really important on that. Okay, so the doctor gives the patient the test. The result is positive. The question is, does the patient really have HIV? So if we were to do the study, which one was the easiest to find?
They already knew.
When you knew they had HIV. But now what situation do we really want to know?
The second one.
Yeah, the second one that's really hard to find out.
Oh, yeah.
Okay, so we now want to know the chance that they have HIV given they had a positive test. And we decided previously that the other way around was much easier to measure, but that's not the probability we want, right? Okay, this is where Bayes' rule comes in handy. So Bayes' rule says, let's take that probability that was easy to measure, take a couple other probabilities and get the one we want. So I can get the one I want without having to do that horrific study we talked about. I can do the easy study, get a few more numbers, and I can have the one I want. Make sense? Okay.
Does that work out perfectly every time, or is that just
It does. It's actually mathematically proven. So there's this nice little slick mathematical proof that shows that mathematically this works out every time.
So,
So, what was that?
I'm sure you'll explain what PA and PB are.
Oh, yes. Okay, so this would be like, I want the probability that she has HIV given she had a positive test. So I can use the probability that somebody gets a positive test given they had HIV, so those are switched, times the probability that someone in the general population has HIV, divided by the probability that someone in the general population gets a positive test. So the.
So that's all, so essentially what's going on is you ran that first experiment to get all of those probabilities.
Yeah, I ran the
Well, at
experiments to
least
get this,
PDA, yeah.
and there may have been separate experiments to get this and to get this.
Oh yeah, that you can
But
just get
these
from.
would be much easier to get than this still. This is almost impossible to get.
Yeah,
But
okay.
these are all something we can get. Because you can just take a whole bunch of people in the population.
Yeah.
And in fact, I don't know if you guys are aware of this. I've had friends who got horribly offended by this because they didn't understand the public health issue behind it. But when a woman goes in, when she's pregnant, your doctor will try to get you to take an HIV test. No matter what, whether you're at risk, whether you're not at risk, no matter what. Why do you think they try to do that? They want those numbers. It's not because they think you have HIV, it's because they need those numbers so that they can deal with patients who actually might have HIV. So although, yeah, it has nothing to do with you, it has everything to do with public health. Does that make sense? So if you go into the doctor and they're trying to get you to take an HIV test, particularly if you're not a risk factor, go for it. I mean, all you're doing is helping the health community.
Is that why they always test your blood?
Better to know.
That our patient has HIV given that they had a positive test if we can find these other three probabilities. Now I will tell you the hardest thing about conditional probabilities is it's so easy to get turned around, and we'll find this on our in-class assignment. You're going to have to be on your toes. And I have learned the hard way to not answer quickly when you guys ask me questions, because invariably I answer wrong and I give you misguided information. Okay. Now there's the medical term for HIV, the chance that you have HIV given a positive test. It actually has a name, it's called specificity. So if you ever hear somebody talk about the specificity of a test, that's what they're talking about. It's the ability of the test to, let me see. It's the chance that you actually have the disease if you have a positive test. That's the specificity.
So it's gonna be different
It's like the
for all the tests.
validity of the test.
Sort of, they're different measures of validity and they have very specific names. So I'll show you a few of the names. And so if you memorize them when you go to the doctor, you'll know what your doctor's talking about. Maybe. Depending on your doctor. Okay, then you have P of HIV, that's the probability somebody has HIV in the population. So that's just, the term for that is prevalence. So that's the prevalence of HIV in the population. That's just how many people in the general population are infected with HIV. And then P positive test, that's just the probability that if you took your population and you just gave them all the ELISA test, and you're not paying attention to who's actually infected and who's not infected, that's the chance that you would just get a positive test. So, okay, so important vocabulary. So here's your vocabulary page for the day. Sensitivity, the chance that if you have HIV, the ability of the test to give you, to detect it. Yes.
Sorry, going back to the slide before. With the probability that a random person will have a positive test, so does that get skewed by whether or not they actually have HIV?
Because we don't know if they have HIV, that information cannot be used to skew the probability. So once we use that information, then it becomes a conditional probability. When we don't, that's the probability they're trying to get when they're trying to make everybody take a test. So even though I have 0 risk factors for HIV, my doctor wants me to take a test so he can get that last probability. Does that make sense? Yes, Shane?
And that same statistic includes those that actually will end up having HIV and those that got a false negative.
Yeah, so those positive tests are all the people who got false positives.
False positives, right?
And people who are infected, whether they know it or not. So they may be infected and know it. They may be infected and they don't know it. They may be infected and get it, you know what I'm saying? So they're not paying attention to the actual infection.
Right.
They're only looking
Just a
at,
positive
did you
test.
get a positive test or not a positive test? So the conditions come in the top two. Okay, so sensitivity means if I have HIV, what's the chance I get a positive test? So in the case of AIDS, what do you want to have be the case for that probability?
100.
You can't make it 100, but you want it to be as
High.
close to that as possible. Because what
99.9.
happens if you are on the other side?
Then you have it in
Yeah, you have people who come in, they got a test, it was negative, they think they don't have the infection, and they do. What are the consequences?
If it's spread,
Yeah, okay, yeah, they give it to other people, and they don't get treatment as quickly as they probably should. So you want that sensitivity up as high as you can get it.
Is that like a type 1 error?
Yes. That's exactly what it is. Specificity, oh, I have specificity wrong on the other slide. Ignore it on the other slide, this one's right. I always get turned around when I'm doing probability. I love probability, but those of you who've had much experience with it, probability is really tough, I think. Anyway. Okay, so it's the chance that somebody comes in and they don't have HIV and they get a negative test. So what number do you want? Do you want that to, how do you want that probability to be?
High.
Yeah, you want that to be really high.
Isn't this the same as type 1 and 2 errors?
Pretty much. This one's not a type 1 or type 2. This is but it's tied in with them. But the first one would be considered a type 1 error. Yeah. Okay, so if you had to pick one of these to be higher, because these play off each other just like type 1 and type 2 error do. If one of these had to be higher, which one would you think would be most important to be higher? Yeah, there's a much greater risk to the public if you send somebody out into the public who is infected and they don't know it. Now, what are the consequences of this?
That's
Well,
like
it's
my
possible the
question.
drugs hurt them.
Someone might get positive when they're not. Make someone really stressed out for no
Mental
reason.
distress.
Yeah, basically the main thing, because they don't stop here. Like if you have a positive test, they don't just stop there and go, let's give you all the treatment. I mean, they have a whole, they continue a series of diagnostics after that.
well, for several college kids who donate plasma, if you get a false positive, you can never donate plasma again.
Yeah, it doesn't matter if they prove later on you didn't have it. You're out of the running for plasma, blood donation, everything, ever in your life, no matter what. There's also social stigma associated with it. So let's say
$60.
you have no risk factors and you get a positive test and you're married. What do you tell your spouse? I got a positive test. And they're like, oh my gosh, because you know how you get AIDS. And you're like, no, I'm sorry, I didn't know. I didn't want to get a positive test. There's a lot of stuff that could go wrong. So the effects of making a mistake here are pretty devastating, but they do consider these to be more devastating than these. But they're both bad. So you want those probabilities to be as high as possible. Yes, right.
So I'm just trying to think, how do they come up with PA and PP? Because that's changing every year.
And they do monitor, like CDC monitors these probabilities constantly, because you're right, the incidence is it's fluctuating. It went way up, and now it's going down again, and now it's going up again. But now they have some new breakthroughs, so it's starting to go down again. You know, and so that's one reason why they're making people take as many people as they can get to take that
So
test.
they are continuously updating their data, and it looked like kind of moving as a range because they have to eliminate old ones but add the new ones, not keep everything, right?
Yeah, CDC employs garbage loads of statisticians. Yeah. Yes.
Now, you say that those statisticians are worth garbage, or?
No, just think of how much is in your trash. Quantity, we're talking volume, not
Oh,
quality.
okay.
Quantity, not quality. Yeah. They hire lots of statisticians. Okay, so, all right, so the incidence or the prevalence, those are two words for just saying how many people in the general population actually have AIDS. And that number is changing constantly. Also, these tests are continually tweaked and fine-tuned, so that probability of getting a positive test is going to change also. Also, it will change as the prevalence increases, because obviously if you have more people in the population who have AIDS, what's going to happen to the probability of a positive test? It goes up too, right? Yeah, so those are tied in together. So yeah, they do. Okay, so now we're going to do the math. I found these numbers. I'm not exactly sure how reliable they are. They're fairly close, but I'm, like I said, as Ryan had mentioned, these are always changing. So a doctor has a patient that has a positive ELISA test. He needs to know the chance that his patient actually has HIV. He has the following information. The current incidence of HIV is 0.6 of the general population right now. The sensitivity of the ELISA test is 99.7. So what was the sensitivity? Because this is how the doctor is going to read it, and this is probably how he'll talk to his patients.
that
It's
you
good.
don't get told that you have it when you do?
This is when
0.3%.
you have it and the test finds it.
Which means, yeah, so 99%
So,
of the time.
You have it, and this is the ability of the test to find it in somebody that actually has it. The paper he read recently said that the chance that a randomly selected individual in the population tests positive for HIV is 1.7%. So if you just globally gave out this test, then about 1.7% of the population would test positive.
So did they just use like a sample and then multiply by the population for the first number? Because not everyone's been tested for HIV, so I'm assuming they like have done this like 1,000 or 10,000 samples and then just multiplied it by the amount of population to find out how many people actually have AIDS.
Yeah, these are estimates obtained from real data, but because you don't have the whole population, and also our privacy laws make getting these numbers really difficult. Like
Sure.
if you live in Denmark, this is public information. Not that they can trace it to you, but if you have HIV, they know every person who's been diagnosed with HIV in that country. It's part of the government records. That is not the case in our country, so getting these numbers is actually really quite difficult. So, yeah, it's interesting to go to these statistical talks and have someone from like Scandinavia talk because their privacy system is so different. That's right.
So I'm just wondering if there's more math that's involved, but could you extrapolate those, using those numbers and say that the ELISA test is wrong 1.4% of the time based on this information?
Well, the question is, what is wrong?
Giving a false positive.
Well, there are two kinds of wrong. There's telling somebody who's sick that they're well and telling somebody who's well that they're
Okay.
sick. We're going to come up, we'll actually find something.
Okay.
But it's saying wrong is more complex than it sounds up front.
Yeah.
It's we can do it, we can find all the wrongs, but it's not obvious.
Okay.
So. Okay, so basically, how would I write these probabilities? What would be the 0.6?
That would be the HIV.
So that's the probability of HIV, right? Okay, what's the sensitivity?
It's the probability of the test.
The positive test given they have HIV.
Right, and we want that to be super high, which it is. This is pretty good for. Okay, what's the next one?
They have a positive test.
Yeah. And what does the doctor really want to know?
What's the probability of it?
Probably HIV is 5%.
Right, he has a patient with a positive test. He needs to know if the chance that they are actually infected. Fishing.
I want to see if I understand this right. So on that last one on there, is that pretty much using that a paper recently read and the current incidence of HIV? If you combine those two, does that mean that more than half of the positive tests are not actually HIV? Because you're looking at 1.7 of them will test positive, but only 0.6 of the population actually have it.
It's more complex than that because you have to keep in mind there are people with HIV who will test negative. So they're not the same group. Like they're,
Yeah,
it's like
okay.
that Venn diagram where they overlap and some are out, and
Okay.
yeah, that's what we're talking about. Okay, so to find the actual probability, we take the test. Okay, so we put in all the numbers, how we have them. What's the chance that that patient actually has HIV? Yeah,
It's not very high.
is that kind of crazy?
Wait, hold on. They had a positive test.
So they go to the office, they have a positive test.
And
What's the chance they actually have HIV?
I wouldn't even tell them if it was positive.
Yeah.
I'd be like, we're just giving you your test because we found
Is that kind of nuts though? Would you think it was a lot higher than that? Yeah, so there's only like a 12% chance you actually have HIV if you get a positive ELISA test. So
Comfort, no?
if this happens to you and you're donating blood and you test positive, or you're the doctor and you test positive and your spouse is freaking out, you can say, it's okay, there's only a 12% chance I actually have it. Actually 13.
So, if I understand this correctly, if you have HIV and you take the test, you're 99.7% probable that you're going to be caught or found. You discovered whatever. Whatever you want to phrase it as. It's going to be discovered that you have HIV. But if you test positive, you only have a 12.7% chance that you actually do have it.
Mm-hmm.
So it gives a lot of false
false positives.
Yeah, so there's a lot of false positives then.
Yes. There are a lot of, so what happens is it's catching a lot of people, it's catching the vast majority of people who actually have HIV. They will learn they have HIV. But in doing so, it makes it so a lot of people who get positive tests don't actually have it.
That's okay.
So
It's
in order
better
to get
careful
that
than-
sensitivity higher, this number goes
Yeah.
down.
Okay.
Okay. Oh, this is What's that?
I got like 35.
So did I. Okay, so I always get Let me check. I always have this particular set of slides filled with mistakes. So, okay, probability of HIV is 0.06.
Oh, are we saying something right?
Are you guys getting 35% too?
Yeah, I just did. Yeah,
My calculator is not working right now. It's broken.
Well, that
I got
actually makes me feel a
35%.
little bit better, because I feel like
Just
it should be more.
running the numbers on the screen like as they are, 35%.
Yeah. Okay, did I get them right from the previous page?
Yeah.
Yeah, 1.7.
Yeah.
Maybe she did this so that we wouldn't be so like.
Yeah.
35
It's like a mind
Yeah.
check.
You're right, I got 35% too.
So like, oh, that's actually really good. And before it would have been like, really, that's horrible. But now,
I don't have your book in here.
So,
Okay,
so
now I'm frustrated. Okay.
35% chance.
I always find that.
Not necessarily better, but more accurate.
Somehow.
oh yeah, they're for the people that are going to blood.
Say, oh yeah, that's so much better.
Okay.
Could you define that for me?
Somebody have their book?
Yeah.
There's two probabilities I consistently mix up, and I left my book in my office, so let me make sure I didn't mix something I shouldn't have mixed
If you're coming from like a
Because you're right, now that I calculated, I'm doing that too. Somebody checked last semester.
Just blame the calculator gods.
Okay, so we'll change that to 35% when we get back. Okay.
I mean, I'm not taking credit.
But still, that's pretty low. Still only 35% chance.
It's still double that.
Yes.
It's hard.
Okay, so the next one. Now, let's say this is one, actually I had a friend who had this happen, not with HIV, but with hepatitis B. She was donating blood and tested positive for hepatitis B. Let's say you're doing a blood drive and they call you and they say, we tested your blood and it tested positive for HIV. And now you want to know the chance that you actually have HIV. So now the question is, what's the population of people you're dealing with? What's the pool you're in right now? Is it the general public, or do we know something about you? Okay, we know you tested positive, but just even before you went in.
Oh, you give blood.
Yeah, so do you think people who get blood are like everybody else?
No.
What do you think their incidence of HIV is? It's going to be lower, because most people who are high risk or have the disease aren't going to be walking into the Red Cross anytime soon. So we're going to assume, so what goes down? Yeah, the prevalence, right?
Which one is that?
So it was like 0.6% of the general population. So the probability that
Okay,
a general population in the blood donating population is probably going to be much smaller than the 0.6%. Okay, so we're going to assume, okay, so we have our sensitivity and specificity, and we're going to change this number to 0.2.
But this is out of just the blood donor pool.
Yeah,
right?
this is the blood donor. Because you went in to donate blood, you've actually made that population smaller. It's not the general public anymore.
You could look at past ones.
What was that?
You could probably look at past ones too. Past blood drives.
But the Red Cross would only keep data on how many positive tests they have.
Oh yeah, that's true.
And,
Oh, okay, yeah, that's true.
yeah. Okay, we're going to do a different approach now than Bayes rule. Because let's say we don't know how often they test positive. So we could find that out. We're going to pretend we don't know what it is. Okay. So what am I going to say here? So what you're going to do is you're going to make a crosstab table like you do for chi-square, but you're going to do it with probabilities. And you're going to put in what you know. Now, first of all, you just make up a big number, like I put in 1,000,000. This number is just made up. Just pull it out of a hat somewhere, okay? I just wanted a big number. And so what I know from my numbers here, we don't know this number anymore. We know those numbers. So we know that out of 1,000,000 people, 2,000 of them would have HIV. Does that make sense? And so if I subtract the two numbers, I find out that 998,000 do not have HIV. Right? And then I also know that if they have HIV, so now I'm only in this column right here. Okay? Is that what we're looking at? Yeah. We know that 0.997 of them, 99.7% of them will test positive. Make sense?
Who have it? Of those.
Yeah, so we know they have HIV. This is how many are going to test positive. Now, the specificity comes in down here. So we know that if they don't have HIV, 98.5% are going to test negative. Make sense? And then we can use that with the 1,000,000 to, with this group. So this I'm taking out of the 2,000 that have HIV. This I'm taking out of the 998,000 that don't have HIV. Does that make sense? I've now restricted my pool.
How did you choose 0.95? I would see how you could do it. If you know that 1994, then you could subtract that from 1,000,000.
That came from here, actually, and I should have written that on the board. So that's the probability that you have a negative test given you have no HIV. Okay, that makes sense? Okay, I should have put that.
But could you figure that out without knowing that? Because, no, even though you know that 1994 of your 1,000,000 people are over there, don't the rest have to be there?
No, because if you add these, you don't have 1,000,000. You have to have at least 2 of these middle squares filled out in order to complete the table.
What's the 2,000?
Okay, so I know that 2% of the population has HIV. So if I take, 0.2%. So if I take 0.002 times the 1,000,000 that I made up, then
The 1,000,000 would be like your pool of
yes.
population.
And the whole purpose of this table is to get probability, so it doesn't matter what number goes here. It just matters that it's just easier to visualize if it's a bigger number. So if you put 10,000 here, it would still work. Does that make sense? So we're going to go through this piece by piece. So yeah, this is how we get for 2,000, and then this plus this has to equal 1,000,000. And so that's how we got this one. Are you guys okay on where these numbers came from? Okay. Okay, so now that these are the numbers we already found, and this is how we're going to find the rest. So to get this number, we just subtract the 2. So we assume that if somebody has HIV, the chance that they get a negative test, only 6 of them will get a negative test out of 1,000,000.
Wow. Not out of 2,000?
Well, out of our pool of let me put it this way. It's 6 out of the 2,000, but it's also 6 out of the whole population will have HIV.
Because the 2,000 of the population are the ones with HIV.
Yeah, out of this 1,000,000, you'll have 6 people who actually have HIV and will get a negative test. Does that make sense?
Okay. So those are the ones that have already tested positive.
Yeah, so if you had a population of 1,000,000 with these numbers, 6 of those people would fall into this category. So they would have HIV, get a negative test, and not know they're infected, even though they are. Make sense? Okay. And then, same thing, we're going to just subtract these 2. So these are the false positives. So how many false positives do we have?
That's a lot.
Yeah, so out of this group, we have 14,970 who don't have HIV, but had a test that indicated they do have HIV.
Have they kind of made the, I'm not a chemist, but have they kind of altered the test so that it will tell people? That doesn't make any sense, does it?
Okay, but I know what you're saying. What happens is these two numbers have to play off each other. If they want this one small, it makes this one big. And if they bring this down, it's going to make this go up.
So they can kind of affect the test so that it at least tells is
Right.
accurate.
They
for the most
over
part.
time they bring both numbers kind of down.
Right.
But typically, bringing this one down requires bringing this one up. And when they consider this one to
So
be
they
the
just
most
work on that
dangerous situation, they drive this down as far as possible and feel bad for these guys. I try to get a good.
Sacrificing.
So you can compare that to a type 1 versus a type 2.
That's exactly what. So this would be a type 1 error, and this is the type 2 error.
And the risk of committing a type 1 error is huge with this.
For committing a type 1 error, it's extremely small. But committing a type
Well,
2
no, but
error.
the consequences of committing a type 1 error.
Yes, they're extremely large, so that's why this number has to be so tiny. So you want to drive that way down. Yeah. Okay, so, and then, like I said, you just add these across to get this number and add these across to get the number. And then you can use all of these numbers to get the probabilities that you need. So, let's say I want the chance that somebody gets, which one am I asking you for? A positive test. We'll just start off with that. How would I find the chance that somebody gets a positive test? Yeah, so I go this divided by this, right? This is all the people in the population who got a positive test divided by the number of people in the population. So this isn't the probability we're really after, but it's
1.7%.
yeah. So pretty much what we had before. Okay, but the probability we really wanted was the probability of HIV given that you have a positive test. So what would be your numerator? Actually, let's start with the denominator. It's easier to start with the denominator. Which number am I going to use to go in the bottom?
Quick question, isn't this also given positive test as a blood donor?
Yes, this is the person who gets called up by the Red Cross and is told that they had a positive HIV test.
Okay.
And now they want to know the chance that they actually have HIV. And hopefully the person on the phone will tell them that. And they don't have to take a probability class to figure it out. So, what am I going to put on the bottom? The denominator is what you really want to look at first. We're just going to use the counts to start off. So which one of these numbers would I pull off the chart and put in this?
16,000.
Right, so, because we're only now looking at people who test positive, right? So this is our group that you now belong to. We know you belong to this group, so we don't need to look at these people anymore.
What's the probability you actually do it?
Okay, now, what do I use as the numerator? Yeah, because I'm only now concerned with this row of people. I only need to worry about these people who actually got positive. So this is the numerator. Okay, so our test, oh yeah, so this is the probability of a positive test.
Okay, so what's that
Yeah,
one?
wait.
Oh, you can ignore the log total probability. I'm not going to make you worry about that.
The numbers were different on the last one, weren't they?
No, that's
That was
actually
the
what
first
you get.
one.
Oh, okay.
Yeah,
Oh, okay.
I rounded.
Sorry, I was
Get a
thinking
positive
together.
test.
Cool. Okay, but your chance of actually getting a positive, let's see if I calculated this one right. Anybody want to check?
That's the number I got.
0.11. How come this one's way different than?
Okay, the reason is because these probabilities are highly dependent on the prevalence.
Oh, that's right.
And because there is hardly anybody in the population who actually has HIV, it drives up those false positives way high. So if you took a different disease like the flu, this number would go way down because this probability would be really, really high. Does that make sense? And this probability would go up also, but because of that, it's going to make this probability a lot higher. So the fact that you only have 0.2% in the blood donor population that have HIV is going to make this false positive rate go way down. I'm sorry. What was I trying to say? I'm saying this backwards. I was going to turn around. The chance that you actually, yeah, your false positive rate is going to go way up, which makes the chance that you have HIV go way down.
So the statistic you originally gave, you had 3, like forever going on your slides. Do you know if that included those that do donate blood, those that get like a false positive?
Well,
That was the
what happens,
entire
the population was just different. It was just the whole population.
Right.
So it included those who
So
donate
it
blood
does
and
include
who
those who
don't
donate
donate
blood.
blood. Yeah. So that was just in general. They weren't asking about blood donation. So they would be included.
I just didn't know if that was a report from hospitals instead of a report from the Red Cross. That's all.
Yeah, I don't know. I know the CDC tracks these numbers very, very carefully. So, and I don't know how recent they are. Okay. So,
Cool.
yes, Jordan.
So, I think I'm blind for a second. This probability of HIV given that you have a positive test that's on the board, when you divide those, you get the probability.
You'll get that same number right there.
Okay, so it's the same thing.
Yeah, it's 2 ways of getting the same number.
Okay, but here you obviously use the original formula we were talking about before, right?
Right, but I did actually get this number off of the table, but you can also get this number off of the table, or you can use Bayes' rules to get it. But either way, you should get the same number. Does that make sense? Any questions? So, our in-class work is on recidivism rates.
Sweet.
It's on a crime report from the Department of Justice, and if you are so inclined, there is the link. And it is, I kid you not, the most recent report on recidivism, even though it's from 1994. So I'm hoping they're doing another one soon.
What is recidivism?
That's the chance you go back. That's when you go back to prison.
Oh,
Like somebody who's released, the chance that they come back to prison.
Okay.
Okay, so we're going to actually do the first part together for practice. And then I'll send you on your way. Well, not on your way. And then I'll send you the rest by yourself. Okay, so if the report found that on prisoners who'd been released, that the percent of the prisoners who had been released that were female was 8.7%. And the percent of prisoners that are arrested within 3 years of release is 67.5%. And the percent of female prisoners who were arrested within 3 years of release was 57.6%. Okay, so how would I write that very first probability? So, is it a conditional probability?
No.
Okay, no, it's not. It's so what? I'm going to use F. So,
Probability of rearrest.
right, so
So
we call
is
it,
it like R?
and next.
0.675.
Okay, and what's this second probability? This is where you're going to have to be careful, because this wording is not the same wording we used in the slides. So you have to figure out what you know and what you're trying to find the probability of.
You find the probability of them being female knowing that they are rearrested.
Let me see.
Yeah, that's right.
So do we know they're female, or do we know they were rearrested?
Just arrested.
Well, for that one, for the 67.
female, that's easy.
Is our population
depends.
people who are
Sometimes it's
rearrested, or is our population females? Is Kayla?
Well, the 67.5% is including both male and female that are rearrested, and the 57.6 is the females that are rearrested. So wouldn't that be our population if we're trying to figure out the females that were rearrested?
Okay, so what goes on what side? Where does female go?
Left.
Right.
The population is female, so this 57.6%, we're taking all the females and we want to know the chance that they are rearrested. So the question is, are you talking about all the people who are rearrested, or are you talking about all the females? And we are talking about all the females, so the females go here.
All right, let's keep rolling.
Okay, so
Number 2. Let's go.
that was A. Okay. You can do B and C just fine, actually pretty quickly. So I'll let you go ahead and do those.
He's just the opposite of what